Okay, let's start to cover organic semiconductor devices. I'm covering it in the light emission portion of the course because a lot of the devices we're going to talk about are light emitting diodes and photovoltaics. So I saved organic semiconductors for this point in the course for that reason. Here's some photos of some of the things you achieve with these type of devices. OLED displays can be thinner than any LCD display, and of course photovoltaics can be made thin in plastic because these are organic polymer materials. But we'll look at some of the advantages and disadvantages. But first, let's start to understand the materials themselves. So, the next few slides are for your benefit, so you're not clueless about the emerging field of organic electronics. If I test you on anything, it will be on basic general information, okay? So I don't expect you to become an expert at this. So, two classes of materials: inorganic materials. That's all the stuff that's not organic. That's how I'm going to classify this. And that's all the stuff we've been talking about up to this point. So if we can classify all the stuff that's not organic as inorganic, then let's just define what organic is. Well, organic materials are defined in some textbooks as containing one or more carbon-hydrogen bonds. And so if you look at an organic molecule like this here, you've got carbon-hydrogen bonds. You've got oxygen, carbon, hydrogen, hydrogen, oxygen, but the most important thing is you've got these multiple carbon-hydrogen bonds. Now in this case, this molecule here's showing the bonding structure, and here's another representation of that. This is vitamin B, okay? Here's another molecule over here which has lots of carbon-hydrogen bonds. This is the molecule that made Starbucks wealthy. What do you think it is? Well, this is caffeine. So you can also see here, this is when you put the atoms in their actual sizes and locations, this represents how they all kind of squeeze together for the molecule. Now, here's something that is important that we understand right off the bat for organic materials. Here's some approximate bond energies, meaning that if I bring atoms together, how much energy will it take to break them apart and break apart their bonds? Well, for something like carbon-hydrogen, it's around 3.5 electron volts. Now, look at gallium nitride and gallium arsenide. 9 electron volts, 6.5 electron volts. That's a big difference. So right off the bat, what does this tell you about organic electronics? What this tells you about organic electronics is that it's easier for them to degrade. For example, imagine if I have sunlight with ultraviolet light comes in with energy of photons greater than 3.5 electron volts, which is the UV light. That would be enough energy to break down a carbon-hydrogen bond. Expose something to chemicals, they can degrade. The big challenge for organic electronics is they tend to degrade more easily. And think about blue LEDs too. If I make blue OLEDs, organic light-emitting diodes, the emission energy is getting really close to the bond energy for these things, and so those become very challenging because if you have any photons or any electron hole pairs with just energy getting close to this, they could get a little bit more energy and have enough to basically start breaking the material down. And so you can see why gallium nitride and gallium arsenide give you much more robust materials compared to organics. Keep in mind, we're talking about the energy to break apart two atoms. We're not talking about splitting the atom. If you split an atom like uranium-235, it's not electron volts, but it's 200 mega electron volts. So that's a whole different classification. So, for all organic semiconductors, we typically have a conjugated bonding, which means we have alternating double, single carbon-carbon bonds. And so if I look at this as a classic example, this is a benzene molecule. I've got carbon, 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 and hydrogen out here. But looking at the carbon bonding, you'll find that carbon here, I have a carbon here. It has two bonds with this carbon. It shares 2 electrons, covalently sharing 2 electrons. And in this direction, the carbon is covalently sharing only 1 electron. Let's first off see for this molecule why we need this alternating single, double, single, double, single, double between the actual atoms themselves. So, go back to silicon. How many electrons does silicon need to fill its outer shell, the magic gate? Well, we know that silicon is in column 4, so it needs 4 other silicon atoms to covalently bond with and share electrons with. And so silicon basically bonds covalently with 4 other silicon atoms, single bonds, and that allows them, each sharing an electron, that allows them to each think that they have 8 electrons. Now, carbon is in the same column as silicon, so we know it also wants 4 electrons to get to 8. But how many shared electrons do you see above here? Well, remember, I've got carbon-hydrogen bonds here, so that changes this scenario. This is an organic material because I've got the carbon-hydrogen bonds. Well, let's count them up. Here's carbon, and I've got 1 with the hydrogen, because hydrogen provides 1 electron that it can share with carbon, so I share 1 that way. With this carbon over here, I share 2, so that's 1, 2, 3, and then 1 here is 4. I've got 4. Let's go over here. 1, 2, 3, 4, and again 1, 2, 3, 4, etc., etc. And so the reason why I have alternating double and single is that's how these things get the number of having 1 bond or 2 bonds on either side to get a total of 4 when they bond with the hydrogen. And so this special conjugated bonding is found with all organic semiconductors, typically. So here's some of the more famous conjugated polymers: polyacetylene, polyphenylene, vinylene, polythiophenylene, polyaniline. There's a bunch of them, and you'll notice that you see all these alternating double and single bonds. Okay. Furthermore, if you look at most fluorescent organic materials, such as fluorescent dyes, they are also conjugated. Okay. So we'll come back to that a little bit later as well. Let's look at the most famous conjugated polymer on the next slide. The most famous conjugated polymer is penacene. Basically, five fused benzene rings. Okay, every carbon atom is seeing alternating double and single bonds. Here's the carbons. Here's the hydrogens on the outside. Okay, here's a beautiful non-contact force microscopy image of a penacene molecule. Here's what a pile of it looks like. Looks like a black powder. And let's talk a little bit about doping this thing. So, most organic semiconductors like penacene can increase their conductivity by something called oxygen doping. So what molecule does the oxygen replace? Well, it replaces the hydrogen. So I'll basically replace hydrogen with oxygen. Now, most organic semiconductors are more p-type because you use oxygen doping. So think about how many electrons are wanted by oxygen versus hydrogen. Hydrogen wants 1 electron to become helium and have a full outer shell, because at the beginning of the periodic table there's only 2 electrons in the outer shell for hydrogen and helium. So it wants just 1. Oxygen wants 2. And so the oxygen takes an extra electron away from the carbon, creating a hole, hence why most organic semiconductors are p-type, because you use things like oxygen doping. So what about band diagrams? Well, let's start with something familiar, which is not organic. Let's look at our silicon atom. And we had talked about before the Pauli exclusion principle, where if here's one atom, here's the various energy levels as you go further away from the nucleus and you go higher in energy, right? And so go further away, I've got these various energy levels that have electrons in them. And this is just showing basically the binding energy to keep electrons in the atom. So if I want to rip an electron and take it out over here, the deeper I go here, the harder it is to get the electron out. Okay? And this is showing distance further out. I'm getting further away from the atom. So this is narrow, this is wider, meaning with distance, I'm getting further and further away from the atom in terms of the location it could be. So one here would be here or here, and one here could be further out here or here. Okay? So bring 2 atoms together. We know based on the Pauli exclusion principle that electrons can no longer be in the quantum state. So when we bring 2 atoms together, all these states split into 2 states as the energy level shifts so that the electrons are not in the same quantum states. We learned this at the beginning of this course, if you recall. Then if you have many atoms, here's an atom, etc. They all talk together quantum mechanically, and it shifts into bands. As all these discrete states start to spread, you end up with a band. Okay? So, the red lines in all of these things, well, in these things here at least, represent delocalized electron bands that conduct. These red lines here. And so why is it only the higher energy ones? Well, if you look at this, this is, electrical potential. Here's an atom. You're trying to get away from this atom if you want to free up an electron. Here's an atom, here's an atom, here's an atom. At these energies, that means the electrons can freely flow between the atoms because they have energy greater than the energy barriers in between them. Okay? So that's all this is showing here in the diagram. Now, let's keep moving in terms of the band diagrams and starting to understand a conduction band versus a valence band, which we don't have in organics, but we'll have something similar. So in an actual atom, the electrons do not orbit in perfect circles. Okay? And so here you have some example electron orbitals for very simple 2-electron, or I think that this might be for hydrogen for this case, but it's some of the first orbitals you have for an atom. Okay? So you've got the S and the P states, and basically the dark and the light colors represent positive and negative phases of the electron wave functions. Okay, so don't go a whole lot into that, but that's just kind of their locations or orbitals they can have in their positive phase or negative phase. And there's a lot more of these. But basically these represent just where you're likely to find the electron. Okay? So, let's say I bring two of these atoms together here with their orbitals. Okay? And the atomic orbitals are for the individual atoms, and here's the energy states. When I bring them together, because of Pauli exclusion principle, they have to shift, right? And so these shift, and what they give me is a bonding state and an anti-bonding state, which provides a molecular orbital. Remember, this is atomic orbitals, meaning energy states for individual atoms. When you bring them together, you get a molecule, which has something called a molecular orbital, which has two different levels here. Now you can see where we're headed with this. This is starting to show us a lower energy level and a higher energy level, kind of like a conduction and a valence band. When I bond them together, all of a sudden a band starts to appear. And this is just an example for bonding of pp orbitals here. They bond together. You get a molecular orbital, which is a pi and pi star. Same thing, they have to shift, and you get something which is going to be two energy levels, which I can transition before. And again, there's many other types, but you're getting the picture at this point. So, let's look at what we get at the end. What we end up for those bonding and anti-bonding state is something that we call a lowest unoccupied molecular orbital and a highest occupied molecular orbital. Think of the lowest unoccupied molecular orbital kind of like the conduction band. Okay? I'm using this loosely as I say this. And the highest occupied molecular orbital is kind of like the valence band, meaning that with no energy, all the electrons will be orbiting the molecule in this state. If I give it some more energy, the electrons can be kicked up to the next unoccupied molecular orbital. They kick up from the occupied molecular orbital. That makes sense. That's where they are, hence why it's called the occupied molecular orbital, up to the unoccupied one. Because if this was occupied, how could you go there, right? So these are the two closest together that allows that first transition that could happen. So here are some different fluorescent dye molecules, and you'll see how this works beautifully here as well in terms of quantum mechanics. And so here's a blue dye in some fluid, here's a green fluorescent dye, and here's a red fluorescent dye, and we're exciting them all with UV light, and we're kicking up the molecular orbitals to the higher energy state, which is the LUMO. And when it comes back down, it emits light that's blue, green, or red. And notice as you go from blue to green to red, that all you have to do is make the molecule larger. Well, why is that? Well, the reason why is these molecules are so small that I can treat them as a quantum well, basically. Consider the electron that's traveling around this thing to be pretty much like an electron in a quantum well. So if I make a larger molecule, I'm making a larger quantum well. Well, if I have a quantum well, as I make it wider, right, then the first energy state comes lower. If I make the quantum well smaller, the first energy state goes up. And so you can already see how the LUMO and the HOMO levels here shift with molecule size, and you can design organic semiconducting molecules to emit light based on their size by treating them like a quantum well where the well width switches, and you can shift the first energy state as a result. So how do we create electron-hole pairs? Well, you don't necessarily have electron-hole pairs in silicon in terms of generating energy. You have something called excitons, which basically means that, let's say I have a electron orbiting a molecule like this. If I give it some energy, it could then, switch to a different orbit like this. But if you look at this now, in this state, this was where the electron was in its average function. When I move it over here, its average function's over here, so I end up with a net positive charge left behind and a net negative charge over here on average, because the electron's spending more time here as it moves away from the nucleus, which is positive. You feel more positive here and more negative here. And that's what we call an exciton, which is basically a higher energy orbit, which gives the appearance locally of having positive and negative charge as the electron's no longer where it was before in its normal electrically neutral state. Okay? So you've got these excitons, light comes in, it's absorbed, it creates an exciton like this as it kicks orbitals into high energy states, and that creates the presence of a net negative and positive charge displacement. How do you move these around? Well, this exciton energy can be transferred from molecule to molecule. However, unlike of other types of energy transfer, the carrier is not free like it is in a silicon. It has to move charge through a bunch of other bumps and orbitals and charges. Remember, molecules are messy, not like a perfect crystal. And this is one reason why mobility in organics are hundreds to thousands of times slower than they are in semiconductors. So it's very difficult to move an exciton across a organic semiconductor device. So what can we do with this? Well, here's some of the advantages of these materials. They can be potentially low cost. I could take something like, if I find an organic semiconductor and I could dissolve it in a solvent, I could spray it onto a piece of plastic and deposit it. So I can make semiconductors that I could put coat onto something as cheap as paint potentially. There's other ways to deposit it. And most importantly, I can put these things down at low temperatures, which means I can grow them on plastic. Unlike silicon, which requires 1,000 degrees Celsius to deposit it, which is way too hot to deposit on something like plastic. So I can start to make flexible, rollable, and highly impact resistant devices, which is really attractive for things like portable displays. This is a rollable display technology shown here. Well, what are some of the disadvantages? Well, we talked about this. The bond energies for organics are much lower than inorganics. And why is this a problem? Sunlight hits the solar cell, it can break it down because it can break the bonding energy. You drive a lot of electrical current through an OLED device, it's trying to emit blue light, could have enough energy to break the bonds. And chemically, these things can be attacked easy because it's easy for chemicals to attack the bonds as well. Also, the mobilities are not as high, so forget about high speed or high current applications. You're not going to find that with organic semiconductors. So what we're going to do next, we're going to take a break, but then we're going to cover OLEDs, OLED displays, TFTs, and organic photovoltaics. So take a break, but do this review first, and then we'll come back and go on to the next part.